Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. This video lesson is going to look at using BatchSep and AspenPlus to do batch distillation calculations. I'm going to ask you to pause and read this problem statement before continuing. I've gone ahead and set up the feed stream. The feed stream, I added the components benzene, monochlorobenzene, and dichlorobenzene. I'm using the UNIFAC equation of state. And I have my feed compositions, temperature, pressure, and we were told in the problem statement that we're going to be using 100 pound moles. Aspen is designed for continuous processes, so I need to put it as a per time. So I arbitrarily selected 100 pound moles per hour. I then added my still pot and two product streams. Now the still pot in the older versions is going to be found under columns. It's normally over here. In version 10, they've moved it so that it has its own little tab for batch models. And we want a batch separation. You can choose any of these pictures you want. I just went with the top one. And so we've just simply added this here. Now, I'm going to give you some fair warning. AspenPlus is designed for continuous steady state operations, and it can work for some transient stuff, but it's based on flow systems. This is not a system with flow, and we're having to treat it as if it is. So notice the flow streams going in and out of something that's a batch. That's going to cause a little bit of awkwardness. It was originally created by a third party, and Aspen purchased this software and is now in the process of adapting it to their normal kind of usage procedures. That means every time you go to a more and more modern version of Aspen, it's going to have changed a little bit. And the handout is in version 8.6. I'm using version 10. You're going to see quite a few differences. So let's go ahead and open up our block and begin looking at it. First of all, in the problem statement, they said that we would have 10 stages plus the still pot. So that means I need 11 equilibrium stages. I would like to have a total condenser, and I only want to deal with one receiver. If I have a choice, I would rather have shortcut heat transfer calculations. I don't need those to be overly rigorous. I would have to have heat transfer coefficients and so forth to do that. And I'm going to, for my initial condition, do it where I'm initially charging material into the pot. So I'm not sure. There, okay, it's working for me. The pot charge is going to be the feed stream. Basis is on moles. And number of receivers, I'm going to do 1, and it is going to be capturing the distillate. I'm not going to have any side draws. The pressures and holdup, well, they specified that I'm going to have 0.02 cubic feet of holdup of the liquid, and so that would be stages 2 to 10. That came from the problem statement. The condenser, I do want it to be atmospheric, but because all my material is stated in terms of PSIA, it is a little bit nicer to be consistent with our units. And I don't have a column pressure drop stated, but I was told the pot pressure was 17.5 PSIA. Okay. Let's just, no, yeah, that would be wrong. And I'm just putting in a guess here that it ought to be somewhere on the order of 17 down at the bottom of the tower. Okay. Not sure why that is still red. The condenser. Okay. Subcooling, I really just want it to be a saturated liquid, so 0 degrees subcooled. That does not mean it's going to that temperature. It means that that's going to be 0 degrees lower than whatever the condensation temperature is. I wanted a total, and you can click on these and look and see what the picture is. If I click on it for partial, it means that whatever vapor is created here will come and be collected with that. So I suppose we might stay with that. And the still pot itself, it's going to ask me to come up with the dimensions of the still pot. Probably I would like to do diameter and volume. Unfortunately, it will not allow me to run until I have this all specified. I could remove my column and come back to it. You could just guess what you think the volume should be. Probably the best thing to do would be to run your simulation with only a feed stream and look and see what the volume is of 100 pound-moles per hour. Now, I've set this up so that I'm using 10 cubic meters pretty arbitrarily and a diameter of 1 meter. Okay, so those are fairly arbitrary choices. You just want to make sure that it is big enough. If you get something and you get an error message, then just change it. Seems to like it better if I say that I'm going to calculate from tray or packing hydraulics, but I really didn't want to get involved in that. So, not sure why it has the red still. This is what I've entered in the past. I'm going to go ahead and move on to some other things and see if maybe that corrects it. If not, we'll come back and figure this out in a moment. Let's come down to heat transfer. So heat transfer, again, I'd rather just do the shortcut. I don't need the full details of what the heat exchanger design should be. You can do it based on if you know how much heat transfer or if you know a boil-up rate. And in this case, I know a mole boil-up rate. And it is based on pound-moles per hour. In the problem statement, it said it was 200 pound-moles per hour with a reflux ratio of 3. So we'll get to that in a few moments. Okay. Initial conditions. So I'm starting with an initial charge. I am going to just put all of my 100 pound-moles in there initially. The temperature is given, the pressure. Ah, 17.5. And I don't know, I'll put just one of the gases in there to fill the rest of the space. You have to have something to fill the space. So I've got that set up now. Setup is still not happy. Well, okay. Let's come on to our operating steps. This is really the key to how to get BatchSep to work, is you have to tell it what you're going to do in which order. So we're going to save our work right here. We're going to stop and come back and we'll complete the video in a second lesson. Thank you.